This morning's speaker unfortunately couldn't come in person, but he's been involved in the space effort for gravitational waves for many years. It's Stefano Vitale from University of Trento, an old friend of mine, and he'll talk for the usual hour and answer questions even though he's distant. So your turn. Take over, Stefano.
Thank you, Barry. Thank you for this kind invitation. Thank you to the Foundation for this opportunity. So today's talk is about LISA, that you may know that is a sort of LIGO in space, same concept. You have test masses and you track relative motion of test masses with a laser interferometer. The main difference is that on the Earth, you're confined to a size of a few kilometers. In space, this is million-kilometer arm length. But the most important difference is that it aims at a frequency range that you cannot access from ground, from a few tenths of microhertz to a fraction of a hertz. You cannot access from ground because the gravitational field of the Earth is too noisy, mostly because of motion of the atmosphere and the Earth crust. And so as soon as you approach a few hertz, as I'm sure many of my colleagues have already told you in the previous day, the noise becomes too large to have any astrophysical interest. So you have to go to space. So let me first start. Well, this is a project which is led by the European Space Agency. I had symbols here. It's led by the European Space Agency, but has a major contribution by NASA. And also, as usual with a European mission, there is a contribution of many member states of ESA in their agencies. So let me start why you want to go to low frequency, why you're not happy with the fantastic success of ground-based detector. The reason I'm sure you have been shown this cartoon of a binary system. The reason why I'm showing it is that the cartoon shows that the frequency of the wave for a binary system is twice the frequency of revolution of the system, right? And the frequency of revolution for a large part of the history of the binary system is given by Kepler formula, certainly within 10%, okay? And Kepler formula has mass and separation of the two bodies. And you know that separation cannot go to zero, right? There is a minimum separation below which the two bodies will merge. I mean, when you have big bodies, low density bodies like the sun, they would never approach that distance. But even two black holes can only approach the sum of the two Schwarzschild radii. And so if you normalize this distance to the sum of the Schwarzschild radii of the two bodies, the formula becomes a decreasing function of the mass, the frequency of revolution, and then the frequency of the wave becomes a decreasing function of the mass and a decreasing function of the separation to final collapse. And this one is a counterplot of this function. And so you immediately get what you achieve by punching through this few hertz wall or the gravitational wave noise. On one side, you access a world of very massive body, while on the ground you can access solar mass up to, say, 1,000 solar mass. Here you access the realm of million or even billion solar masses, which means these supermassive black holes, which mostly means the supermassive black hole that we now know are hosted in the center of almost all galaxies we know, actually probably all galaxies. So this is an old animation. Is made by collating pictures of the center of our galaxy. And so this is a Nobel Prize of a few years ago. You see stars rotating around nothing. The nothing is a supermassive black hole of a few million solar mass. And we now know that all galaxies have this black hole in the center. The larger the galaxy, with a tendency, the larger the galaxy is having a larger black hole. Now you see galaxies interacting. This is an animation from the Hubble Space Telescope that connect a few snapshots of interacting galaxies, and the people calculates that when two galaxies approach each other and start interacting gravitationally, what is in reality forming is a binary of the two black holes in the center of their galaxies. So this is a scaled up version of the fantastic sources that Barry and his colleague have been detecting now for quite a few years. And it's on steroid, right? Because you remember that the amplitude of the gravitational wave signal scales with the mass of the two bodies. And so these signals are huge. They are very energetic. I think you have been already told that they release on the gravitational wave more energy than the entire universe in the same time in the electromagnetic sector. What you see here is a simulation of LISA data with no filtering, right? With just the low-pass filter you need to download the data to ground. And so you see this would be a small pair of black hole at a redshift of 15, so in deep universe, and you would see on an oscilloscope, as an experimentalist would say, right? So very large signal. For some of those, the signal-to-noise ratio will exceed the 1,000, and will stay in the 100 area even at a redshift of 20. So basically, the limit of the certainly beyond the limit of the electromagnetic observable universe. And because this guy spin down, right? While they orbit, they spin down, and their frequency increases. Sooner or later, they enter the LISA band, as this cartoon shows. Whatever their mass, for variable amount of time, they will enter in the LISA band. And so what the people hope to do with an instrument like LISA is to do a sort of cosmological stratigraphy, right? Where you see these binary events back and back and back in time. And so you reconstruct the formation of the nearby galaxies by mergers of older galaxies back in time down to the limit of the universe. And the hopes are that through this stratigraphy, we will be able to reconstruct what was the original source of these black holes, what were the seeds. There is a lot of studies on merging the information that we will get from an instrument like ET for the small black holes, LISA, and their electromagnetic counterpart in a multi-messenger scenario that should be able to tell us how these big black holes have been forming from smaller seeds, right? So that just to give you a flavor. I'm not a theorist, right? So I make a disclaimer about accuracy of what I'm saying. I just communicate my feeling. Another interesting another interesting observation that we expect to do connected with the supermassive black holes is the capture of a small object like a small black hole or maybe a neutron star by one of these monsters, right? And the people calculate that the small object will orbit the supermassive black hole for 100,000 orbits. You see, the orbits is very non-Keplerian. It's whatever, but it's not a plane orbit, right? It's very chaotic. And I'm now showing you a simulation where the gravitational wave signal has been converted to a sound. Is very much accelerated, right? Because this is very low frequency, as I told you. But and then I want to comment this. So this is the... And so you see, the first thing you notice is that the signal disappears suddenly. And that's because the guy falls into the event horizon, and then not even gravitational wave can get out of the event horizon. So this, is the signal is very, very rich with a lot of content that allows you to map the gravitational field nearby the event horizon, and it also shows if there is in reality an event horizon, and if we got it right, that these guys are really black hole. Just as a curiosity, recently X-ray mission, this is one case from XMM, have detected flares, periodic flares of X-rays that might be one of these guys orbiting the big black hole and going through the accretion disk. And when it passes the accretion disk, it emits a flare of X-rays. So we could be witnessing the formation of one of this extreme mass ratio binary, as they are called, in the making. As I was telling you, this is a fantastic general relativity laboratory or fundamental physics laboratory, because the people hope to be able to calculate the orbit, calculate the signal you expect in general relativity, and any deviation from this, anything that says that there is more than just the mass and the spin in the central body, will have a specific fingerprint in case it is due to some strong environmental perturbation, or is some exotic compact object but still in general relativity, or if we are witnessing some deviation from general relativity. So very rich signal with very rich physics. With black hole, you can do cosmography. I'm sure somebody has spoken to you about the fact that a gravitational wave carry the information, the spinning, the time evolving gravitational wave carries the information of the distance to the source. That's because obviously the rate of change of the period gives you the energy of the signal at the source, while you measure the energy of the signal here, and from the ratio you get the distance. And so people hope, unfortunately, this is redshifted information, so you don't know independently the redshift of the source, you only know the luminosity distance. But if somebody tells you the redshift, then you can do an independent mapping of the redshift to luminosity distance plot, which is the basic equation of state of the universe. In the early days, people thought, I'm sure you heard, because you can do the same things with a massive side of the black hole with the ET. That's what we hope to do. This will, LISA will instead work with many different sources, the supermassive black hole at big distances, this capture of small objects from the central body at intermediate distance, and even the LIGO black holes when they are still in their revolution phase. In recent years, the people have demonstrated that you don't need to individually know the electromagnetic counterpart of all these sources. You can do a fit to the electromagnetic picture of the universe that should give you a good resolution on the equational state of the universe. But don't ask me too many questions, because you will discover the level of my incompetence. So this was, up to now I told you big masses. The other one is non-transient sources. From ground, basically, except maybe sooner or later we will see some asymmetric source. From ground, we only see transient, right? The last few seconds of the evolution of these systems. From space, you can see things that are so separated that they are basically stationary sources. Most of these sources are binary in our galaxies. These are small objects, so the signal is not very intense, and so they must be close. And so this is the realm of binaries in our galaxies. Mostly white dwarf binaries, right? And I'll tell you a little bit more. But also the typical sources for LIGO, Virgo, and Kagura, so binary black holes, for instance, in our galaxies, but in a phase where they are still detached much before the final collapse. And I'll tell you the fascinating possibility that this opens. So the standard binaries, the situation looks like that. LISA should be able to discriminate tens of thousands of different binaries. That's because LISA lasts for years, so the resolution, the spectral resolution is microhertz, and so the frequency of these sources is separated by more than microhertz, and so we should be able to discriminate tens of thousands. Some of those, the ones that are represented here, are well known. We know them optically. They are visible, and so we know the period, everything. And so in the old days, we call this verification binaries. It was the big selling point of LISA before the discovery by Berry and colleagues. We have the signal guaranteed. Nowadays, they are very important to calibrate the instrument. And so these are there, will be seen, and the resolution with which this will be seen will calibrate, in a sense, the instrument. The other one, the 20,000, the tens of thousands, will be one of the most massive survey of the galaxies. You must figure out that the largest part of this object are not visible in the electromagnetic sector. And so this is a simulation of the catalog of binaries. These are only the binaries superimposed to the Gaia picture of our galaxy. These are so many that unfortunately, or fortunately, because it depends on who you talk to, there will be a foreground of these signals that you cannot discriminate. So it's a sort of glow of the galaxy which will superimpose to the other source. It's a disturbance for some of the signals, and is a very interesting signal in itself. I could speak hours on this, but I just stole a few slides from one of my colleagues, Valeria Corral, on what the astronomer expect to do with this additional probe on the formation of the galaxy. So you see, they for instance, they hope to see satellites to compact object, and even to discover exoplanet orbiting this object. But very large astronomy investigation field. Just one last thing on these detached sources before I go back to my real field of expertise, which is the instrument. Some of the sources, as I told you, will be active both in the field of LISA and in the frequency band of LISA and in that of the terrestrial detector. Very soon after the black hole, LIGO black hole, was detected, one of our colleagues calculated that if LISA had been up in the air, it would have been detected, the signal from this same black hole in its detached phase for years before seeing a signal disappearing from the LISA band and reappearing in the LIGO band a week later, roughly a week later. So this looks like a curiosity, or I would have seen it, but it's not. The more the sensitivity of the ground-based detector will increase, and so in the ET era, a big fraction, more than 10% of the signals detected by ET will also be detected by LISA. And the people immediately calculated this gives an enormous power for instance, in measurement of deviation from general relativity. You're observing this source for years over 4 decades of frequency, and this is a very rich signal that allows for very accurate tests of the underlying theory of gravity. Obviously, the data analysis is a nightmare because, contrary to the current ground-based detector, where signals are isolated, one per week, maybe one per day, here the signals are on at all times, right? So the data analysis is a gigantic fit to the entire set of data. The people are playing with that, have demonstrated that it's possible, heavy but possible, and if you want to join, there is an ongoing effort since few years, and with many years in the future of doing this data challenge, where a group in secret prepare a set of synthetic data for LISA, and then they make it public, and you can practice detecting this signal, and then you compare what you have detected with a true image of the universe that went into the data. And if you want to know more about the physics of LISA, these are the white paper our 3 science working group have recently delivered, one on astrophysics, one on cosmology, and one on fundamental physics. They are on the archive, and I think they will be all published in the Living Review on General Relativity. Okay, I survived the science, so let me, I'm a plumber, so let me go back to the instrument. How you detect how LISA works. So you know what a gravitational wave is and what a gravitational wave detector is. In space, the effect that matters is the following. You know that the gravitational wave, if you send an electromagnetic beam from an observer to another observer, that's the basic concept of LIGO, the frequency of the beam crossing the gravitational wave gets modulated, right? Modulated in time. LIGO people speaks of the phase of the electromagnetic wave, but in reality, the real signal is encoded in the variation of the frequency, right? The frequency of the wave oscillates because the gravitational wave modulated. And actually, it is the time derivative of the frequency which is proportional to the curvature tensor of the wave. I'm sure that by now you know everything about that. This formula is for my general talk. It also shows that the larger the detector, the larger is the effect on the frequency modulation. Now, the reason why I'm showing this is that in the space environment, it's very popular to measure the Doppler effect on an electromagnetic beam propagating from a satellite to ground, for instance. That's the way the celestial navigation people, the satellite navigation people, steer their satellite. They measure the velocity and the distance by looking at the Doppler effect on a transmitted wave. So, in a sense, the classical connection between a satellite and ground is the way to detect gravitational wave. You send a beam from a satellite to another satellite, in the case of LISA. You measure the frequency of the beam here, and if there is a frequency modulation, this might be a gravitational wave. So the basic complement to measure the basic complement of LISA is two satellites, 1 and 2 satellites, exchanging an electromagnetic beam. And if there is a gravitational wave passing by, you see the frequency received modulated relative to the frequency. Think of a perfectly stable frequency of the laser, and you would see it modulated, okay? And LISA, you cannot do this with one arm for the same reason you cannot do on ground. It would be nice, but lasers are too noisy. I'll come back to that. So you need at least 2 arms, and to do 2 arms you need 3 satellites, and once you have 3 satellites you also close the 3rd arm. It would be stupid to just stay with 3 arms. These 3 satellites go around the sun on standard orbit. It's a magic of celestial mechanics. You can put 3 satellites in 3 heliocentric orbits like those of the Earth, and just working on the inclination of the orbit and a little phase shift, they will go forever in a triangle with good approximation, let's say with 1% distortion, without the need of using engines, right? You don't need to push those satellites to form this triangle formation. This triangle formation is very important because it rotates in the gravitational wave and allows you to reconstruct the position of the source in the sky with comparatively high resolution. So, in principle, that's a complement. You send a laser beam. I don't know if you see the animation, but the animation is this satellite, the emitter, sends a laser beam to the satellite, which is the receiver. This guy measures the frequency, he sees the frequency changing, represented with a dramatic change of color in this cartoon, and he concludes that there is a gravitational wave, and the signal is proportional to curvature. But you all know very well that there is another much more mundane way to do a Doppler effect, which is shake the source or shake the receiver or shake both. Any acceleration of the receiver or the emitter relative to the local inertial frame will cause a a time-varying Doppler modulation of the light. And unfortunately, and so the signal is the superposition of your gravitational wave signal and also the difference of acceleration of the receiver and the emitter. And unfortunately, very soon in the game of thinking to a space-based detector, people discovered that a satellite in an orbit more or less where we are, at the same distance of the Earth, is subject to solar radiation pressure. And solar radiation pressure is not stable, so it oscillates in time, and so will accelerate the satellite, and those accelerations would produce frequency modulations that are much larger than the ones that are of astrophysical interest. So, big problem. What we do? So what we do was discovered pretty fast. You carry an inertial reference to correct for the spurious acceleration of the spacecraft. This inertial reference is a test mass which is free floating in the spacecraft. It doesn't touch anything, and because it's in the spacecraft, it's shielded from solar radiation pressure. So the spacecraft shake because of solar radiation pressure, but the test mass which is inside the spacecraft is untouched, and so continues to navigate gravitationally. How you do that with avoiding collision? You do that by measuring where the test mass is in the spacecraft and with an interferometer, and you feed back this information to a set of micronewton thrusters, of little thrusters, rockets, that keep the spacecraft centered on the test mass to avoid collision. So your test mass now is navigating undisturbed, and so it's purely gravitational, or at least better than the satellite, and the satellite is noisy, but you can now measure the acceleration of the satellite relative to the test mass, and if you do a little math, you know this acceleration, right, because you have measured. So with the local interferometer, you measure the difference of acceleration between this test mass and the spacecraft. You do the same thing here. Then you measure the separation or the acceleration of the two spacecraft, which contains the gravitational signal. And I think you have to do this plus this minus this, let's see. Yes. And then the spacecraft cancel out. The acceleration of the spacecraft cancel out. And you're left with a signal which is the same as you had done the scheme of sending a laser beam, but from one test mass to the other test mass that are now much more quieter. Obviously, the acceleration of the test mass will damage your signal, and that's one of the major entries in LISA noise, but they are much smaller than the one of the satellite, and so the instrument is now a good instrument, right? So this is one of the first tricks of LISA. Now, one privilege of Barry and his colleague is that he can send the light back and forth in one LIGO arm many, many times, right? 100, accumulate energy, right? And so the basic LIGO thing is 2 mirrors, right? Unfortunately, over 2 million kilometers, if you send a 1 watt of light, reflect back on a mirror, the size even of the spacecraft, and get back, you get a few tenths of photons per second. So no way. So the concept of LISA is that you do 6 of this frequency, one-way frequency measurement. You send a beam from this spacecraft to this one, you collect the light here and measure the frequency, doing interference between this beam and a local laser. And you do the 6 signals, and you mix these 6 signals to synthesize an interferometer. And I'll tell you a little bit more later. Actually, no, I'll tell you a little bit more immediately. You know that this laser interferometer, lasers are miserable, right? You're trying to discriminate the gravitational wave signal. If you describe it as a modulation of the frequency of the laser, is a few microhertz over the terahertz of the infrared radiation, right? And if you take any laser and you do very good stabilization, you end with kilohertz per root hertz noise, right? So you have to detect microhertz and you have kilohertz. So what do? You would see only the frequency variation of the laser if you do this naively. So what you do on ground is that you send the light on two equal length arms. So whatever is the frequency of the light here at the beam splitter, the light travels for the same time, and so when you compare the light that is coming from the same arm, whatever was the frequency was the same for the two. So if there is a frequency change between the two, it's due to something that has happened in the arm. Maybe acceleration of the mirror, but hopefully a gravitational wave. And I think, Barry will correct me, I think LIGO arms are equal to a millimeter, something like that, but I may be wrong. In LISA, arms are equal to 100,000 kilometers, which is not very nice, right? And so you have to synthesize an equal arm interferometer by recombining the light, by combining the 6 signals so that you artificially reconstruct a beam, 2 beams that have traveled for the same time between the 3 spacecraft. This is a space-time diagram of the 3 spacecraft which are in a plane, so you can do a 3D space-time diagram. To do that, you need to know when one of the signal received and one of the satellite left the original spacecraft. And so you need to know the distance between the spacecraft at an absolute level. And oops, I think I'm missing one view graph. And to give you a feeling, I'm missing one view graph, and I'll tell you just in words. But synthesizing this thing, you start with a signal. If you just would do a one-way measurement of the frequency, your noise would be here. If you do a two-way measurement of the frequency, you somehow suppress the thing, and you would be here, right? If you just combine 2 arms, subtracting most of the propagation time, but you're still with this 100,000 kilometer, a third of a second of travel time of the light, you would be here, and you need to be here. So this synthetic combination of arms to make an equal arm interferometer has to suppress, 6 orders of magnitude noise, and this is one of the key things of LISA interferometry. The picture I'm missing, sorry, it was a mistake. The picture you're missing is that to do that, you need to know this travel time with 1 meter accuracy. And we measured that with an internal GPS. So on the same laser beam, we beat a pseudocode like the GPS does, a sequence of characters. You receive the beam here, and you also receive the sideband with a pseudocode, and you slide your local pseudocode until the correlation is maximum. That's what the GPS does, and you reconstruct the absolute distance between the 2 spacecraft. And the calculations show and the simulations show that we should be at a few centimeter level while we need meters. So this is one of the good things. Obviously, you need a very good measurement of phase, and the demonstration that you can do this very good measurement of phase has been done on ground in many labs, and comparing beams coming from 3 different sources and delaying them until you can beat the frequency noise of the common laser. And here, you see the frequency, the phase in one of those interferometer that you have to read here, 10 to the 12 microcycle, and you see the difference between the 3 combined with right delays that you have to read here, which is directly microcycle or 100 of microcycle, and you see that the noise has been suppressed by a very large dynamic range. Oh, here I had the thing. Sorry, but I already told you this GPS picture. Okay, now I think I'm going a little bit too slow. So let me give a look to the LISA instrument, but I can recover later. Let's do a little look to the LISA instrument. So this part here, what is in reality this cartoon here consists of. So at each end of one of this beam, you had one of this instrument, which is formed by the test mass, which is in reality a device surrounded by a lot of accessories, an optical bench on which you do all your optics, all your interferometry. So it carries the local interferometer to measure where the test mass is, and it carries the interferometer to do the spacecraft-to-spacecraft measurement, and it carries a telescope which is needed to collect the light from a distant spacecraft and to send the light to the distant spacecraft. This is not to look at stars. So this is the test mass. I can show you because we flew two on LISA Pathfinder, so this is real flight hardware. It's a gold-platinum mass. I'll tell you more later. It sits in this hole here without touching anything, right? When it is in flight, it's suspended with millimeter all around, 3 to 4 millimeter all around the thing. It's surrounded by electrodes because unfortunately you can let the test mass free of moving along the direction of your gravitational wave measurement, but because you have two in a spacecraft, you cannot leave it free in all directions, and so in all other direction, you push very gently electrically with this electrode by putting a little electric field, and so the test mass is surrounded by this electrode housing. The optical bench, where all the interferometers sit, is a very complex thing. This is a model is one of the various prototypes under development at Glasgow. Is zero Dewar with this silica bonding technique. I'll come back to that. But to give you an impression, this optical bench is the equivalent of one of the big buildings of LIGO, right? All the interferometer is sitting on these 40 centimeter plates, and all the interferometer is doing there. So I cannot show you the current design because we are in a competitive phase, an industrial competitive contract. I'll come back to that. But the latest or some shadow engineering we do with the LISA consortium, this is how the complement would show in reality. This is the telescope. The test mass will be, and the optical bench are in this box here. And for each satellite, you have two of those pointing to the other two satellites. And this is an old animation, but I think it's still very effective. It shows the telescope. It shows the light being collected by the telescope, distributed on the optical bench, and part of this light goes back to the test mass, which is sitting in a Russian doll series until the beam gets reflected on the test mass. Sensitivity. What limits LISA sensitivity? Well, at low frequency, I already told you, we isolated the test masses. We do our best. Still, there will be disturbances that will accelerate the test masses, much less than the spacecraft, but still consistent, and this will limit the sensitivity of LISA at low frequency, right? Don't you worry, this is one of this cartoon with I think you have seen many times, the spectral density in terms of gravitational wave strain. You have to measure the frequency, so you will have the interferometry noise, which you may see you may describe as a readout noise of the true motion of the test masses. But this only sets at high frequency. I will not speak very much of this, actually, not anymore. And you have to consider that LISA is a low-frequency instrument, and so most of the signal-to-noise of all the sources is accumulated here, where the acceleration noise is dominating or competing with the interferometry noise, right? So the acceleration noise was one of the key technological challenges to be faced by LISA. Let's put a number. These are the requirement of the residual acceleration of these two test masses, right? they shall be less than this line here, right? By now you should be familiar with things per root hertz, but forget the root hertz. These are meters per second square. So acceleration, right? So the acceleration of gravity on the Earth is 10, right? So you're talking requirements that are less than a femto g. There is no way you can demonstrate that on ground. On ground you have 1g, so when there is tilt and motion, so no way. You can demonstrate probably 10 to the minus 8 at some very high frequency, right? And even low Earth orbit, the gravity of the Earth imposes some constraint that makes the instrument very noisy. So even at the time we went with LISA in the ESA system, the only thing in sight was a mission for geodesy up here. And then ESA flew another mission here. You see these are many orders of magnitude for what you need for LISA, and even a very fancy mission in the equivalence principle test that flew after we flew LISA Pathfinder, because it's in a low Earth orbit, as much worse performance that we had. So ESA said, yes, we love LISA, it's a great idea, but how can we give you $2 billion if you're not sure that this is going to work? We are ready to give you some money to demonstrate that it can work, right? That you can isolate test masses so that the relative acceleration due to mundane forces is less than this femto g. And the community converged very quickly to the fact that to demonstrate that you don't need a 1,000,000 kilometer separation, and so that the ideal complement to demonstrate this was to squeeze one of the LISA arm into one single satellite. And so to put two test masses in a single satellite, so instead of 1,000,000 kilometer, half a meter, and measure the relative acceleration and show that they are quite at the level you need for LISA. And so this is the complement we flew. That's called LISA Pathfinder. It's two test masses in a single satellite and two interferometers. One measured the acceleration, the relative acceleration of the test masses. So this is the key science accelerometer. But also another interferometer that you use to measure the position of one of the test masses relative to the satellite, to practice this system of following the test mass with the satellite that you need in LISA. Unfortunately, here you have two test masses that you have to chase in the same direction. That's impossible. So contrary to LISA, we were forced to put a little force to keep this test mass with the other one. We pay a price. The test is more noisy because of that. I'll tell you more later. So that's the complement we flew a few years ago. It's two test masses, gold platinum, which is very dense. 5 centimeters is 2 kilos, right? Very, very, very heavy, very homogeneous, very non-magnetic, and a very high stability zero-dur optical bench that carries the entire interferometry, both the test mass to test mass interferometry and the local interferometer. Electrode housing around the test mass. Oh, by the way, this is exactly the same complement that will fly on LISA. So no, it's not a proof of principle. We decided we fly the same hardware so that we can recycle the hardware. So we carry the electrodes also because we need them both in LISA and in LISA Pathfinder. We carry other things. For instance, there is no wire to electrical ground, right? So the test mass will keep charging up because of the cosmic ray, and you have to get rid of the charge lest it becomes very noisy. And so we carry UV light to neutralize the test mass by steering photoelectron to or away from the test mass. You need to block the test mass at launch because launch is a very dramatic event, and the 2 kilos free with millimeter around will crash everything, will grind your instrument. And you even have to enclose everything into a vacuum can because you have to prepare the vacuum on ground, and I'll tell you more later on. So this complement goes into the central cylinder of a dedicated satellite. And if you want to see the hardware, this is the test mass and the electrode housing. All this was integrated in the vacuum enclosure with the caging mechanism. And by the way, remember that this is the end mirror of an optical system, and so had to be aligned to micron and sub-millirad, and the industry did a fantastic job integrating that. That's the optical bench. This is built with the same technique with which LIGO weld the suspension wires to their mirrors. It's called silica bonding. You put a little sodium dioxide between the hydroxide, between the two components you have to join, and you basically form native material, which is very high stability. You get very few seconds to align, a minute to align the component, and then it's done. If you have made a mistake, you throw out $1 million out of the window. And this also needs microns and sub-millirad, and they made a real jewel. So you see, this is the component being integrated into the satellite. Very complex, unbelievable that you can make such a complex thing to work, but it did work. And so you see here a sequence of picture of the thing being integrated in the satellite, put in the fairing of an Ariane Space launcher. This is the Vega launcher, which is fabricated in Italy. Launched in December 2015. Then we navigated to a sort of interplanetary orbit around a Lagrange point of the Earth Sun system, which is 1.5 million kilometers from the Earth. We navigated for a month. Then we uncaged the test mass, right? We caged with 1,000 kilos this test mass that then we had to release in orbit. Not at all guaranteed we could do it. It was a complex mechanism to release this with very high precision in orbit, basically a second launch campaign. And so you see my usually very serious project manager, Cesar Garcia, cheering the success of this second launch campaign. Everything worked out. To me, that I was not a space guy, this was all magic. So what we were requested to demonstrate and what we did achieve. These are the LISA requirements. I'm running late. These are the LISA requirements. You shall be in acceleration below this yellow line. ESA said, well, I don't want to spend a fortune on this mission. Let's follow the common practice in engineering. Get within an order of magnitude from what you have to go, and the rest will extrapolate based on what we learn. And so they relaxed the requirement by factor 10 in amplitude. So you shall be here, not here. But even more important, they say, we don't care low frequency. Show me at millihertz and we'll be happy, and extrapolate to lower frequency, even because at least at the millihertz is still a very interesting instrument. What were we expecting to do? We calculated what we were expecting to do. The LISA Pathfinder performance budget was a book of 300 pages. But they were front runner, and the front runner were three. This damned electrical actuation we have to do, electrical force we have to do on one of the test masses. You produce a force with an electric field, and to do that you need a voltage generator, and voltage generators are noisy. And actually it turns that the more force you want to apply, for the same noise of the voltage generator, the more force noise you do. Actually, it depends on the setting. If you set the system to compensate a maximum force of so much, you get so much noise. If you double that force, you double the noise. At this intermediate frequency, we were expecting to share the same problem with all our colleagues in gravitational wave, which is Brownian noise. In our case, it's the residual gas around the test mass. You do vacuum. Your vacuum is not perfect. The residual collision of the molecules with the test mass make noise, and this is a flat noise, is white noise. And then at the high frequency, you're limited by the fact that you're using an interferometer, and this interferometer is noisy, and the higher the frequency, the less the motion of the test mass, and so your readout noise becomes dominating. We didn't need a picometer interferometer. We would have done with nanometer interferometer, but what helped? We flew a mission to demonstrate LISA technology, and so we decided to demonstrate picometer per root hertz sensitivity interferometer. And so the combination of that was the dashed line, and on day first of operation, we were at low frequency, we were exactly where we predicted. The Brownian noise, there is a little free parameter, which is the pressure, come back to that. But basically where we predicted, except for the interferometer, which was much better than what we could demonstrate on ground. When we flew it, it was at femtometer level instead of picometer, tenths of femtometer instead of 10 picometer, limited by intrinsic noise sources. And we have a recent paper on this. So a fantastic interferometer. But the most important thing is that at low frequency, we had predicted the noise, and it was better than requirement. So big success. We could have shut the instrument there, go home in glory. But, you ask why we have to apply so much force, because you're limited basically by this force noise due to the electrical field. And so the reason why we had to apply the force is the following. This big chunk of material pulls this test mass with a big gravitational force. If you don't do anything, this test mass will start accelerating and hit the wall of its housing, right? So the approach we took, and if you try to compensate this with an electrical force, all of it, too much. It's too noisy. There is no voltage generator quite enough not to spoil everything. So we took a two-step approach. We measured the mass and the position of all elements of the satellite down to screws, calculate the gravitational field, and put a massive compensation mass made of tungsten, which is almost as dense as gold platinum, to compensate most of the field. Obviously, you compensate to zero, but you make mistakes, right? You have error in positioning the elements, error in measuring the mass, mostly error in positioning. And so the name of the game is how much can be the error? And so calculating all the errors, simulating everything, and so on, we concluded that our acceleration would have been a fraction of a nanometer per second square, plus or minus, you don't know, so you have to prepare to compensate any number in this range. But we went up and we discovered that we meaning industry and scientists and so on, had done a much better job and had quite a bit of sheer luck. So instead of 650, we only did 25 in the scale. So we could crank down the maximum force we were prepared to compensate. And so going from the 650 to 50, we went down to where the red dots are, which are better than LISA requirement. And then we really basked in glory and excitation, right? Notice that in the meanwhile, here, where you're limited by the Brownian noise, the things improved spontaneously because we are venting to the outer space, and so the pressure kept going down. So you have a plot here of that plateau as a function of the time from the venting, which reminds exactly the behavior of a vacuum system when you open your pump, right? So the Brownian noise kept going down, and by the time we ended the mission, we had reached the level where we had margin on LISA requirement. We had big margin on LISA requirement all over the place. I was prepared to tell you all the other experiments we have done with LISA Pathfinder. Here are the papers on all this experiment. There are other 3 papers in the coming. There will be more. Sophisticated experiment testing this and that aspect of the noise budget of LISA. I had prepared discharging, the whatever, but I have to jump everything. Sorry about that. Even detecting micrometeoroid, because we can measure the acceleration of the spacecraft when a micrometeoroid hits. So we have even a paper which is relevant for the people that study interplanetary dust. But obviously the most important thing we achieved is to demonstrate that the acceleration is compatible with LISA. This is a simulation of the acceleration in one arm due to a black hole. I can't read, okay, you read the black hole binary on the top of the slide, right? So the blue is the acceleration due to the gravitational wave signal, the equivalent acceleration. The red is LISA Pathfinder noise, right? If you want to see that this is noise, you can zoom in and you see its noise. So you realize the signal-to-noise ratio, the potential signal-to-noise ratio for LISA that we have demonstrated with LISA Pathfinder. And so it's not surprised that even before we ended the LISA Pathfinder operation, ESA decided, okay, let's go with LISA, right? And so in June 2017, LISA was selected as the third large mission of the Cosmic Vision program. And we have run phase A, which is, the main study. We passed with flying colors the review. And this is a slide of a few months ago where it shows that at the end of 2023, we should have the mission adoption review. Adoption means ESA says, okay, let's go, and gives a big contract with a big industrial contractor to really implement the mission. Since then, ESA has decided to accelerate, at least for a quarter of a year, but also to accelerate the following schedule. This is for programmatic reason, and with another mission with some difficulties. And so we now plan to have this adoption to do the review in the third quarter of next year, and to be adopted within next year. And so after you're adopted, you march toward the launch. When the launch is mid-30s, because it takes around 10 years to implement a mission like this. Unfortunately, in this phase, this studies, ESA gives two contractors to keep a little competition. So I cannot show you what the progress on the LISA design, but LISA is a very stable concept, so don't expect surprises. And here is some picture from a shadow study that ESA and the scientists are doing. The technology is under active development, but remember, it must be ready next year, because you don't adopt a mission if the technology is not ready with a certain level of maturity that is nicknamed TRL6. While you're enjoying that cartoon, I keep telling you this, or unless you have a very clear path to reach that technology. What I'm showing with the cartoon is the fabrication of the LISA Pathfinder optical bench. We had a few components and was done by hand. And I told you, every time you put a component, you get 10 minutes to do everything. And if you do something wrong, you start all over again. And these are $1 million that are going away. The LISA optical bench is much more complex. Fortunately, recently, is not so much complex as we thought. I stole this from a talk I had yesterday from the Glasgow group, which is studying the LISA optical bench. This is the number of components of the LISA optical bench over the years. This is the number of components of the LISA Pathfinder optical bench. So fortunately, it's not 80 as it was. They made a dramatic simplification of the design. So this is almost exactly as the component of LISA Pathfinder, with a difference. They are on both sides of the optical bench, while on LISA Pathfinder was only on one side. And you have to fabricate 6 of those because you have 6 optical benches. So no way you can do this by hand. So the system is putting a lot of effort in making this a robot fabrication facility. And you see here the hexapod that should measure where the various components go and do this in an automated way and reliable way. There are other details, but very few things are not a TRL6. This is not a research project. It's now a mission. So beginning the end of next year, all this has to be solid and demonstrated before you start to build the flight hardware. Here are other components that are in this final stage of the development. These are in particular is the slide with the components that are under development in the US under NASA funding in various places, chiefly the telescope and the laser, the very key things. Very good progress. A few worries we had have been recently dissipated, so this is very promising. This is the charge management device that has been already tested on LISA Pathfinder. This has been now moved together with the team to the US. We have to change the source of light, but it's nothing dramatic. So as I told you, this is ESA and NASA and the member state, and this is a cartoon showing more or less what the roles of the various member states. You see that there are many member states. Germany, Italy, Spain, and France and UK are a bit the leading one, as expected. But then we have Belgium, the Netherlands, Poland, the Czech Republic, Denmark, and they are all contributing to this thing. Both the people that contribute to the hardware and the people that prepare for the science exploitation and the data analysis, we all sit in a consortium. The consortium has now 1,600 members. Well, it's a big thing, and you're very welcome to join. And you find it on the web, very easy, and you're very welcome to join if you're interested in LISA. We are running LISA Symposium. You may notice the number is 14. It's a biennial symposium. It's running while we're here. That's why there are a few LISA students in your audience, because this is a big symposium, and there are another 2 days to go. And it's all recorded on YouTube, so if you're interested, you can join to YouTube. I had even prepared beyond LISA, and for instance, it's important for you to know that China has 2 different projects, and sooner or later they will merge in one and plan to do a major space project, maybe in the same time scale of LISA. That would be a great thing to have 2 detectors at once, because you can do correlation, but I have no time to go into detail. And ESA has recently done a perspective study of what to do after this cycle mission, and a follow-on LISA is among the mission that will be considered by ESA in the 2050 timeframe, which is more or less around the peak of your scientific career. So if you want to know that, go on ESA side and look for the Voyage to 2050 exercise. And I think I'll stop here. I think it was 1 hour, right? Okay, so I think I made it. Thank you very much. And I'll take questions, obviously, if anyone can hear one.
If anyone wants to ask questions, please come forward to the podium.
Whoever is speaking, you're muted to me, so I can't hear anything.
Yes, Professor, this was on purpose. We're waiting for questions.
Thank you.
Hello, Professor. Thank you for this talk. So I have a couple of questions. The first one is like more science question, which you. So it is in your first couple of slides where you talk about this scalar tensor theories of gravity to test them with LISA mission. So,
Okay.
So
this one.
Yeah, I think one of these slides.
Oops. Too fast? Yes, okay. I'll come there. Just ask the question and then
Okay. So if we take an MRE system, so which consists of 2 black holes, so can it emit a scalar radiation? Because my understanding is that due to Price theorem, there cannot be any scalar radiation from black holes. So in the MRE system, can we have a scalar radiation? And if yes, it will be a family of circles. So what should be the position of the small black hole to have the maximum chance for detectability?
The honest answer is I have no idea. I can tell you that this is a list of things that is taken from one of the documents. Notice that this is a scalar tensor theory, so this doesn't mean necessarily that we are talking of scalar radiation, but it's perturbation to the tensor radiation due to the scalar tensor theory, right? I think that's the idea. Certainly an instrument like LISA is not sensitive to scalar radiation, because scalar radiation would compress and dilate the instrument, and you have to do differential measurement, and you're not sensitive to that. So like LIGO, LISA, all this differential interferometer would not be sensitive to scalar radiation. So I think what this list of possible alternative theories shows, it means that if you have one of these alternative theories, including scalar tensor radiation, you would see deviation from the predicted quadrupolar radiation predicted from general relativity. So it's not detection of scalar radiation, that's what I mean.
Okay, thank you. And the second question is like you mentioned about this Chinese mission which will be launched approximately at the same time. So how...
Well, no, that's going too far. They hope. That depends very much on when LISA launches. That depends very much when LISA launches. Let me see. Okay, it depends very much when LISA launches. If LISA must have, where we are now, LISA must have a very large delay, and the Chinese must be very fast to have substantial overlap. They still hope to be fast enough to have a few years of overlap with LISA, and we all hope, obviously. They are not yet at the stage where LISA is, mostly because they didn't have a full-fledged LISA pathfinder and a many years design, so they have to make up for a large starting delay. They have flown a few demonstrators that only demonstrated low-level components, and they have yet to decide which project they fly, because one project, the one you see on the right here, is what is called Taiji, which is just LISA, right? It's more or less LISA. The other one is slightly different. It's in an heliocentric orbit. The satellites are in an heliocentric orbit. It's a much less sensitive. It's more dedicated to higher frequencies. So if this flies at the same time of LISA, the overlap will be less significant. If this flies at the time of LISA, then the overlap is very significant. It's more or less like having LIGO and Virgo.
Okay, fine. Thank you very much.
Sure, my pleasure.
Thank you, Professor, for your talk. I want to ask you if LISA can decompose the polarization modes of the gravitational waves it will detect.
Yes.
Yeah, and can it probe potentially new polarization modes beyond general relativity?
Oops. So the answer to the first question is yes, and the reason is in this cartoon. Basically, with 3 arms, you can form two semi-independent interferometer that are turned one relative to the other by 60 degrees, which is not the ideal 45 degree, but is very close. So with the 3 arms, you have these 2 different signals. In addition, LISA rotates. Many of these signals are long-lasting. Even the binary black hole merger lasts weeks, right? And in this week, LISA rotates and probes different orientation in the wave. So it is definitely sensitive to the different polarization. Can they discover new polarization mode? Well, that I don't know, because I never read a paper on this, honestly. But remind, I'm a plumber. I'm the one that brings the screws and the bolts. Did I answer?
Thank you.